Hello learners, on behalf of Indira Gandhi National Open University, we welcome you for this video lecture session. Today's topic is illustrative examples of vapor power cycle. I am Subhashish Maji, professor in Mechanical Engineering of School of Engineering and Technology from Indira Gandhi National Open University. The topic is illustrative examples of vapor power cycle. This is 28th module of the course Thermodynamics and its application. Dear learners, let us begin our discussion. After listening to this video lecture, you will be able to understand the concept of steam power plant. You will be able to explain various vapor power cycles and you will be able to solve the numerical related to various power cycle. Dear learners, in our earlier discussion, we have discussed various vapor power cycle. Now we will solve the numerical related to various vapor power cycles so that your concept will be crystal clear. Let us begin a very interesting problem, that is exercise 1. What flow rate of steam is required to produce 600 kilowatt from an adiabatic turbine with inlet conditions of 800 kilopascal and 400 degrees centigrade and exit conditions of 6 kilopascal and X is equal to 95%. This is the block diagram for the numerical, and here you see an adiabatic turbine is shown. The state 1 is the inlet of the high pressure, high temperature steam at the turbine. So the pressure is 800 kilopascal and temperature is 400 degrees centigrade. At the exit of the turbine, that is state 2, the pressure is 6 kilopascal and the quality of steam is 95%. Let us see how we can proceed for this interesting numerical. Enthalpy at state 1, that is H1, we can get for this particular pressure and for this particular temperature from steam table. So H1 is equal to 3265 kilojoule per kg. The specific volume is given as 0.3842 meter cube per kg, and at the exit of the steam from the turbine, that is at state 2, H2 is HF plus X2 HFG. Enthalpy at the liquid line at pressure 6 kilopascal and HFG will be the value of the latent heat at pressure 6 kilopascal. All these values of HF and HFG you will get from the steam table. So you can very easily calculate H2, that is equal to 2447.08 kilojoule per kg. Now in this expression, m dot n is the rate of mass entering into the steam turbine and m dot 2 is the rate of mass leaving out from this turbine, and for steady state condition, rate of mass entering into the turbine is equal to the rate of mass leaving out from this control volume, that is equal to m dot. So the expression will be m dot multiplied by h1 minus h2 is equal to w. Now dear learners, you see we know h1, we have already calculated h2, the W dot is given for this particular problem, that is 600 kilowatt. So put the values of H1, H2 and W dot. You can calculate the rate of mass entering into the turbine. That comes out to be, for this numerical, is 0.733 kg per second. So this is the final answer for this numerical. Now I have already given the guidelines for solving any numerical. First of all, you first draw the temperature entropy diagram or the block diagram, and you see that what are the data given for this problem. Jot down those data and see how to proceed any particular numerical. Now let us start the second numerical. The second numerical is a steam power plant operates on simple Rankine cycle. The dry saturation steam enters the turbine at 200 bar and leaves it at 1 bar. Calculate the cycle efficiency and number 2, power produced by the turbine for a mass flow rate of 10,000 kg per hour. Now, as I have suggested, first you try to draw the temperature entropy diagram or at least the block diagram so that you can proceed for solving this problem without any difficulty. This is the simple TS diagram. We call it temperature entropy diagram, and the simple steam power cycle on TS plane with saturated steam at inlet to turbine is shown in figure 2. So the figure 2 is the temperature entropy diagram for this particular numerical. So point 3 is the entry point of the turbine and point 4 is the exit point of the turbine, which is also the entrance of the condenser, and point 1 for this particular problem is the exit of the condenser, that is also the entry point of the pump, and state 1 to state 2 is the process which is occurring in the pump, and point 2 is the entry point of the cycle at boiler, and point 3 is the exit point or state 3 at the outlet of the boiler. Now let us see how we can proceed for solving this numerical. Here, what are the things which are already given? That is P3 is equal to 200 bar, and that is at the saturated vapor. So point 3 is on the saturated vapor line. So for that particular pressure, you can calculate the enthalpy from the steam table. So you will get the value of H3 from the steam table for this particular pressure, that is P3 equal to 200 bar. Now, it is an isentropic process which is occurring inside the turbine. So entropy at point 3 is equal to the entropy at point 4. But the entropy at the point 3 you will get from the steam table, because point 3 is at the saturated vapor line. So S4 is equal to Sg is equal to 4.9269 kilojoule per kgK. So entropy at this point 3 is known. That entropy S3 is equal to the entropy at point 4. So now let us see how we can proceed for this particular problem. At the outlet of the turbine, the pressure is 1 bar. So V1 is equal to Vf is equal to 0.001043 meter cube per kg, and for this particular pressure, that HL is equal to HF is equal to 417.46 kilojoule per kg. This information you will get from the steam table for pressure 1 bar. Now HFG is equal to 2498.0 kilojoule per kg. This information you will also get from the steam table. Same thing is for SF and SFG, you will get from the steam table. So process 3-4 is isentropic. As I have already mentioned that S3 is equal to S4 is equal to SF plus X4 SFG at 1 bar. Now dear learners, what is X4? X4 is the quality of steam at the exit point of the turbine. So you know very well the value of S3, you know SF, you know SFG, only one equation and one unknown. You can very much easily to calculate the value of X4. For this problem, X4 is equal to 0.594. Once you calculate X4, there is no difficulty for calculating the enthalpy at state 4, that is H4. So H4 is equal to HF plus X4 HFG at 1 bar. Dear learners, for all these enthalpies of HF and HFG, you will get the information, or for the values of HF and HFG at 1 bar, you can get from the steam table. And if you put all these values in the expressions for H4, you will be able to calculate the value of H4 is equal to 1768.6 kilojoule per kg. Now the pump work WP is equal to V1P multiplied by P2 minus P1, that comes out to be 20.75 kilojoule per kg. But you have to be very careful while putting the values and the conversions of joule to kilojoule. If you want to convert joule to kilojoule, you know very well that you have to divide by 1000. Now we have to calculate heat added. So heat added, that is QH, is equal to H3 minus H2. So that is equal to 2408.7 minus within bracket H1 plus WP, because H2 is equal to H1 plus WP. Now dear learners, you know very well that at this juncture we know H1, we know WP, there is no problem for calculating the heat added, that is QH. So QH is equal to H3 minus H2. Finally you will get the value of QH is equal to 1970.49 kilojoule per kg. The turbine work is WT is equal to H3 minus H4, but if you put the values of H3 and H4, finally you will get the turbine work is equal to 640.1 kilojoule per kg. Now the cycle thermal efficiency eta thermal is equal to net work by net input. The net work is equal to WT minus WP, that is turbine work minus the pump work. All these values at this point we know WT, we know WP, we know QH. So if you put all these values, you will get thermal efficiency is equal to 0.3143 or 31.43%. The power produced by the turbine is equal to m dot WT is equal to 10,000 multiplied by 640.1 divided by 3600. So finally you will get the power produced by the turbine is equal to 1768.6 178.06 kilowatt or 1.778 megawatt, because if you want to convert kilowatt to megawatt, you have to divide by 1000. So 1778.06 kilowatt is equal to 1.778 megawatt. Now let us start the exercise 3. A steam turbine uses 14,000 kg of steam per hour and develops 2,600 kilowatt as shown in figure 3. We will see the figure 3 later on. The steam enters the turbine at 40 bar 400 degrees centigrade. The exhaust steam is condensed at 725 millimeter of Hg when the barometer reads 755 millimeter of Hg. The condensate temperature is 30 degrees centigrade. As it leaves the condenser, the cooling water temperature rises from 0 degrees centigrade to 18 degrees centigrade. Determine the quality of steam entering the condensers and the quantity of circulating cooling water. Dear learners, I have already requested you that when solving any problem, first we have to see what are the data given for that particular problem. After that, we have to draw the temperature entropy diagram or at least the block diagram for the system so that we can solve the problem without any difficulty. Now let us see how we can proceed for solving this very interesting numerical. So this is the adiabatic turbine, and the state 1, the pressure and temperatures are given as 40 bar and 400 degrees centigrade, and the turbine is producing 2,600 kilowatt of power and it is living at the point stage 2. So at 40 bar 400 degrees centigrade, the enthalpy at state 1 we can get from the steam table, and for this problem you will get H1 is equal to 3213 kilojoule per kg and work done in the turbine that is given equal to 2600 kilowatt. Now let us proceed for solving this problem. Quality of steam entering the condenser. This is the first part of the numerical. Condenser pressure is equal to 755 minus 725 equal to 30 millimeter of mercury, that is equal to 30 divided by 1000 multiplied by 13.6 divided by 10, because we know very well that pressure is equal to rho g h. What is rho? That is the density, and density of mercury is known, and g you can take 10 meter per second square and h is given as 30 millimeter of Hg. So if you put all these values and do the proper conversions of the unit, that is equal to 0.0408 bar or 4.08 kilopascal. From steam table at 4.08 kilopascal or 0.0408 bar, the enthalpy at the liquid line is given as 121.5 kilojoule per kg. HFG, you can get the value for HFG from the steam table at 4.08 kilopascal, and this is equal to 2432.9 kilojoule per kg. Now H2 is equal to HF2 plus X2 multiplied by HFG2, but here X2 is the quality of steam or dryness fraction of the steam at the pressure 4.08 kilopascal. So H2 is equal to 121.5 plus X2 multiplied by 2432.9, that is at pressure 4.08 kilopascal. Now we will use the energy balance equations in turbine, and the flow rate which is given as 14,000 kg per hour, we have to convert the flow rate in kg per second. So we have to divide by 3600. So finally the energy balance equation is 14,000 divided by 3,600 multiplied by, within bracket, 3,213 minus, again bracket starts, 121.5 plus x multiplied by 2,432.9 bracket close equal to 2,600. Now what is x? X is the dryness fraction, that is equal to 0.995. So for the second part of this problem is calculations for quality of circulating water. So that we have already got, that is the x is equal to 0.995. Now we have to calculate the next part of this numerical. So before that we have to calculate the enthalpy at state 2, that is H2 is equal to 121.5 plus 0.995 multiplied by 2,432.9, that comes out to be 2,542.23 kilojoule per kg. So you have got the enthalpy at state 2, that is H2. Now we know very well that when there is a heat transfer between a hot body and a cold body, we can say that heat loss by condensing steam for this case is equal to heat gain by the cooling water. Now if you write down the expressions accordingly, let us see what expressions we are getting. Now from heat balance equations we can write Ms multiplied by H2 minus Hc is equal to Mw Cpw multiplied by T2 minus T1. Of course Tw2 T is the temperature, the final temperature of the circulating water inside the condenser, and Tw1 is the initial temperature of the circulating water in the condenser. If you put all the values, there is no problem for calculating Mw. So Mw is equal to Ms multiplied by H2 minus Hc whole divided by Cpw multiplied by Tw2 minus Tw1. So if you put all the values in the right hand side, you will get the value of Mw, that is equal to 806765.88 kg per hour. Now let us see how we can solve the exercise number 4, and you see that all the problems are almost equal and the same type of problems. Only thing we have to first see what we are going to do and how we can do it. First of all, you have to draw the temperature entropy diagram so that things will be very simple for us for solving any problem. So for this problem, a Rankine cycle operates between pressure 80 bar and 0.1 bar as shown in figure 4. The maximum cycle temperature is 600 degrees centigrade. If the steam turbine and condensate pump efficiencies are 0.9 and 0.8 respectively, calculate the specific work and thermal efficiency. So here P1 is given as 80 bar and T1 is 600 degrees centigrade. So H1, S1 you can get from the steam table. H1 for this case is equal to 3642 kilojoule per kg, and S1, that is the entropy at the state 1. So S1 is equal to 7.0206 kilojoule per kg. Since it is an isentropic process, so S1 is equal to S2, and with this equation, that is S1 is equal to S2, but S2 is equal to SF2 plus X2 multiplied by SFG2, you can calculate the dryness fraction or quality of steam. For this problem, it comes out to be X2 is equal to 0.8 0.85. So at this point we can calculate the enthalpy of H2, that is H2 is equal to HF2 plus X2 multiplied by HFG2, and HF2 and HFG2, you can get these values from the steam table. Finally you can calculate H2, that comes out to be 2225.36 kilojoule per kg, and actual turbine work is equal to efficiency of the turbine multiplied by H1 minus H2. For this case, since 90% turbine efficiency is given, so actual turbine work is equal to 1275 kilojoule per kg. Pump work is equal to VFG2 multiplied by P1 minus P2. All these values are given. P1 is given as 80 bar and P2 is also given, and for this case if you put all these values you will get pump work is equal to 8.0272 kilojoule per kg, and actual pump work is equal to 8.072 divided by 0.8, that comes out to be 10.09 kilojoule per kg. So specific work is equal to 1275 minus 10.09 is equal to 1264.91 kilojoule per kg, because the net work is nothing but turbine work minus pump work. So thermal efficiency is W net by Q1. Q1 is equal to H1 minus HF4. HF4 is equal to HFS plus pump work. So HF4 is equal to 191.9 plus 10.09 is equal to 202 kilojoule per kg. So thermal efficiency, if you put the values of W net and Q1, you will get the thermal efficiency for this case is equal to 0.368 or 36.8%. Now we will take up the last problem. The last problem is, in a Rankine cycle, the steam at inlet to turbine is saturated at a pressure of 35 bar and the exhaust pressure is 0.2 bar as shown in the figure 5. Determine the pump work, the turbine work, the Rankine efficiency, the condenser heat flow and the dryness at the end of the expansion, assuming flow rate is given as 9.5 kg per second. So this is the same kind of problem we have already discussed. First of all, we have to calculate the enthalpy H1 that we can get from the steam table for the pressure 35 bar, and point 1 is on the saturated vapor line, and the entropy at point 1 is equal to entropy at point 2. So S1 is equal to S2. With this information you can calculate the quality of steam at point 2, and you know very well the values of enthalpy at point 3, that is on the saturated liquid line for the exit pressure, that is 0.2 bar, and you know very well the quality or the dryness fraction. So there is no problem for calculating H2 and H3, and you can calculate the pump work. After that you can calculate H4. So with this, after calculating the enthalpy at point 1, point 2, point 3 and point 4, there is no problem. But for this problem, let us see how we have calculated all the desired questions for this particular problem. So at P1 is equal to 35 bar, and obviously X1 will be 1, that is on the saturated vapor line, and at P2 is equal to 0.2 bar. So H1 is equal to 2802 kilojoule per kg, and SG1 is equal to 6.1228 kilojoule per kg, and at 0.2 bar HF is given, HFG is given, and there is no problem for calculating H2 once you know the dryness fraction. So for this case, the pump work is equal to VF multiplied by P4 minus P3, that comes out to be 3.54 kilojoule per kg, and the power required to drive the pump is equal to 9.5 multiplied by 3.54 is equal to 33.63 kilojoule per kg. The turbine work. So first of all, we have to calculate the dryness fraction. I have already mention how to calculate the dryness fraction, but for this case x2 is equal to 0.606 and enthalpy at state 2, that is H2, you can calculate once you know the dryness fraction. For this problem, H2 is equal to 1681.31 and the turbine work you can calculate on the basis of this formula given as m dot multiplied by H1 minus H2. You know H1, you know H2, and for this problem we will get the turbine work as 10646.55 kilowatt. The Rankine efficiency is nothing but net output by net input, but for this case you know that net output is equal to H1 minus H2 and the input is H1 minus HF4. All these values are known. For this problem, if you put the values, you will get the Rankine efficiency as 0.44 is equal to 44%. And the condenser heat flow is given as m dot multiplied by H2 minus HF1. Put the values of H2 and HF1 and finally you will get 13,583.20 kilowatt. And the last problem is dryness at the end of the expansion in the turbine, that we have already calculated, that is equal to 0.606 or 60.6%. Now we have discussed all the numericals. Now let us summarize the discussions. We have discussed the concept of steam power plant, we have discussed various vapor power cycle, and finally we have discussed the numerical related to various vapor power cycles. So thank you very much.